In this video we're going to be learning about haloalkanes, in particular the chloroalkanes. They are not a particularly exciting group, apart from the fact that they're a very good precursor for making other organic compounds, in particular the amines. So what I've got here is an example of chlorobutane, 1-chlorobutane I should say, which is CH3, CH2, 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 Cl. Now, even though this carbon-chlorine bond has quite a big difference in electronegativity, so delta minus on the chlorine, it's not a big enough difference for chlorine to be able to make hydrogen bonds with water. So the only way that this could dissolve in water is if it is a polar molecule itself. So what I'm going to do now is just quickly show you whether it is or is not polar enough to dissolve. So I've got just some tap water here. Probably should use distilled to be more careful, but speed. And I'm just going to add my haloalkane to this. I'm not sure if you can see that, but there's two distinct layers there. So it can't dissolve at all in water. So as I say, this is because it can't make hydrogen bonds with the water. It just hasn't got an ability to do it. The main thing that we need to know about these haloalkanes is that first of all, how to classify them. So this is what we call a primary, because the carbon that the chlorine is bound to is only bound to one other carbon. So they're classified, the same way as alcohols. So a secondary would be something like this. Two-chlorobutane would be a secondary alcohol because 2 carbons are bound to the one with the chlorine on it. So that's how they're classified. The other thing that you need to know is how they're made. And you'd expect they'd be quite easy to make. Maybe you just add hydrochloric acid to an alcohol and nucleophilic substitution occurs. And that's a very common mistake, people thinking that that's all that's required. What's really needed is a saturation of chloride ions. So there's not many things that will give us this. But it is indeed a case of reacting an alcohol with something with lots of chlorines. The most common reagent that we see is one that we met when we did the alcohols, and that was the Lucas reagent. That is zinc chloride. I'll do that one down here actually, because I prefer to put it on the top of the arrow. Zinc chloride dissolved in concentrated hydrochloric acid will indeed work, but really only for tertiary and secondary. Its reaction rate is so slow for primary that it's not really used. But luckily for us, there are some other reagents that will work. One of them is called thionyl chloride, and that will make this. And if we notice what's left over, there's an O, an H, an S, and a Cl. And the other O. The two O's and the S go together to make sulfur dioxide, and the H and the Cl that's left over make that. So you can see that you'd need to do this in a fume cupboard because two of your products are pretty nasty acidic gases. Another one that's quite useful is PCl5. And this one here again makes our haloalkane. The H stays with that O and goes with the P and the rest of and some of the Cls. Sorry, start again there. It doesn't go with those. The P goes with the O and some of the Cls, so it's POCl3. The H goes with one of the Cls. So you'll notice that we always have got HCl being driven off. So the easiest way to balance these is to do your acid chloride and your HCl and then see what's left over and they go together. There is one other way to do this, which is with PCl3, but I'm not going to go through that one because what that actually makes, we kind of teach it wrong in level 2, because in level 3 we'll refine it and balance it properly. So I'm going to leave it at just those two and reminding you that there is the Lucas reagent as well that works for secondaries and tertiaries. So you've got 3 different ways to make them. You need to know how to name them, and you need to know that they're a starter. They're a really good starter. You need to remember that they are insoluble in water or immiscible because they cannot form hydrogen bonds.